This is the background material on the lab called Solubility Equilibria. As this implies, the lab that we're going to be doing today still involves equilibrium, and we're going to be using equilibrium to talk about how soluble a substance is. So what's good to know for the lab today is the concepts that it's going to introduce aren't really going to be anything new. You're going to be doing a titration to determine the solubility of something. So we have to revisit what we mean when we're talking about equilibrium. So here's a generic reaction involving a solid breaking up into two ions, and the fact that we have AQ here means that it's in water. So here's some water, and here's the solid sitting in the solution. What happens with this solid over time is as it dissolves, it breaks up into ions. We have A and we have B. It keeps dissolving until it reaches the point where the water is holding as many ions as it can at the particular temperature. At this point, we have reached a state where the solution is now saturated. As these ions float around, sometimes they will collide with each other and they'll reform the original solid. So that's what's being shown right here. So not only do we have the solid dissolving and becoming ions, we have the reverse happening too. We have the ions coming together to make the solid again. And when the rates of these two processes match up, you have reached equilibrium. So we use an equilibrium arrow here. Now we can set up the equilibrium constant expression. So we have the concentration of each of the products on the numerator. On the denominator, we would have put this reactant here, but it's a solid, and solids don't have a concentration, so they're excluded from this expression here. So we have the concentration of A times the concentration of B at equilibrium. If a substance is more soluble, there's going to be more of those ions present in water. So what happens is the value of the concentration of A is higher, and the value of the concentration of B is higher. What happens after that is when you take two numbers that are bigger and you multiply them, that gives you a bigger value of the product, represented as K. So although this is the same exact equilibrium constant we've been talking about all along, we're using it to talk about how soluble a substance is. So one way of using the equilibrium constant is a way to measure solubility. So the relationship is, as the value of K increases, that means that the substance is more soluble in water. You can dissolve more of it in water. So because we're talking about solubility here, we're going to put a little abbreviation down below, and that abbreviation is going to be SP. This means solubility product. So what this is, even though it's the same equilibrium constant, it's called the solubility product constant. This value is often used when we have a salt that's slightly soluble in water. What we typically see when something is slightly soluble in water is a value of K, SP, that's relatively small. So for example, here are some examples of those numbers. Here are some salts, and the thing they share in common is that they all contain barium. The KSP values vary, and you can see that there is a very big difference in these values. At the highest, we have 5 times 10 to the minus 3. At the lowest, we have 3 times 10 to the minus 23. So again, what this number means is that the bigger the number is, the more ions that are present in water, so therefore the more soluble the substance is. The higher the number, the more soluble the substance is. The substance you're going to be working with in lab today is in your kitchen probably, and it's called cream of tartar. The chemical name of that is potassium hydrogen tartrate. That's what the tartar refers to. So it has a relatively complicated molecular structure. It looks like this. We're really not going to deal with the molecular structure here. But what's important to know is that when you put this into water, it dissociates. The potassium ion breaks off, and then this tartrate unit separates. So we have these two separate ions here. Potassium's positive, and then overall this ion right here is negative. But we're not going to represent that like this. We don't really need to look at the structure. All we need to do is abbreviate this. So potassium hydrogen tartrate is going to be called KH-tar. Tar stands for tartrate. When it goes into water, it breaks up into these two ions and it reaches equilibrium. So here is our reaction at equilibrium. We can write the solubility product constant for it, and it's going to look like this. So in order to figure out this solubility product constant, we need to know the concentration of both of these at equilibrium. Well, how are we going to do that? The way we're going to do that is use this ion. This ion is an acid. H tar is an acid. This is the proton that it loses. We are going to react it with a base, and we're going to know the concentration of the base. That's going to be provided to you. So when we react this acid with the base, sodium hydroxide, we get this series of products. But what's important is not necessarily the products we make, it's the ratio between the H tar and the sodium hydroxide. It's a 1-to-1 mole ratio. So this represents both reactions we're going to be working with today. And what's really important to identify is the fact that every single substance we're working with today is in a 1-to-1 mole ratio. There are no coefficients other than 1 here. So from this reaction, we can determine the concentration of H tar. That's going to be done by a titration, and we'll talk about that in lab. Then the question is, well, if we know the concentration of this, how do we know the concentration of potassium? And the answer to that is going off of the mole ratios. If we know how many moles of liter of this we have, we must also have the same number of moles per liter of potassium ion. They're equal to each other because, again, they're in a 1-to-1 mole ratio. From that, we can calculate the value of KSP. So that's one way to represent solubility product constant. So you're going to calculate that to determine solubility, and we're also going to calculate solubility in a different unit. Another way to show it is in terms of grams of this KH tar solid that dissolve per liter of solution. The way we can calculate that is we start with the concentration of KH tar. Well, how do we know that? We know the concentration of H tar, we know the concentration of K plus. Again, everything's in a 1-to-1 mole ratio, so everything's in a 1-to-1 molarity ratio. So what that means is, if we know the concentration of H tar, the amount of KH tar that dissolves is equal. These two are going to be equal again. This is going to be moles per liter, but we want to express it as grams per liter. So the way you convert it is you take this concentration, again, it's the same as this, and you multiply it by the molar mass of KH tar. The molar mass of KH tar is 188.17 grams per mole. This number can be found on page SE2 of your lab manual. So overall, there are going to be two goals of the lab today. We're going to look at the solubility of KH tar at around room temperature. It's around 20 degrees. Solubility does depend on temperature, though. That's important to remember. So we're going to look at solubility of KH tar in water. Another part of the lab you're going to do is going to be looking at the solubility of KH tar with something else there. And the something else that's going to be there is going to be KCl. So that's also going to be in the water. And what we're going to discover is how the solubility of KH tar is affected by the presence of KCl. So this pretty much summarizes what we're going to do in lab. When we get in the lab, we're going to talk about how to set everything up. So that's going to be the first thing we talk about when we get into lab. See you then.